Today we are gonna start the first manufacturing process, which is called machining. It is an important process, important manufacturing process, because it's a versatile process. We can make many things by machining, especially if those things are in a smaller quantity. The process can be automated, especially nowadays with advanced CNC. The machining process can be automated, but still it advised that it is a good process for lower quantity, not for large, making large numbers of parts, which we will discuss it shortly. And also many other processes such as forging or casting or maybe powder metallurgy, they still depends on machining, because after making a part, let's say by forging or by casting, maybe the surface quality is not satisfactory, and we have to do extra process, which machining can be one of those extra process. All right. So let's see, what is machining? Well, in a simple word, we call the removing of material to form a shape, to make a shape, or to modify a surface, we call it machining. So the key then is removing materials. So in contrast with machining, we can mention AM, which stands for additive manufacturing. In additive manufacturing, we are adding layers on top of layers to make things. But in machining, we are removing layers. So these two are the opposite manufacturing processes. All right, so as I show in this image, we can, like in this image, we can consider like the work piece and a tool. And let me see if I can play the video. And I also post this video so you could watch it before the lecture. So this is a like high-speed machining process, removing the material. So the tool is moving, or maybe the tool is fixed, the workpiece is moving. Let me try to play it again. So the workpiece is, or the tool, one of these, there is a relative motion between these two, and you can see the material being removed. This is metal, is steel being removed. But the way that this video shows, we think it's maybe butter that has been removed. Anyway, in this picture, let's say we call this one the workpiece. So this is the workpiece, and this is our tool. Then we can say this surface is the surface that has been machined, and this is the original, let's say, surface. All right. If I draw a line which is like tangent to this tool approximately, and also maybe another line to be perpendicular to the surface that has been machined. This angle is an important angle which we can control it by the way that we hold the tool or adjust the tool. We call this angle rake angle. All right? And the way that the material is being removed is by getting the material to its plastic deformation and breaking point by shearing stress. So as a matter of fact, there are like layer of shearing stress on these lines, and which remove the material. So on each of these layers, we can imagine there is shearing stress that remove the material. All right. So why this rake angle is important? So let's imagine that we are maybe cutting a piece of butter. Let's say this is a piece of butter, and let's say with a knife I want to cut a piece of this butter. Hope you guys are not hungry. Maybe after the class you can go and get, or maybe during the class, get a piece of butter and bread and make yourself a nice sandwich. So, but let's say that we are using a sharp knife, maybe something like this, to, let's say, cutting these butter. So let's say I want to cut this butter along this line, right? So I want you to visualize, if you decide to cut this butter along this line, you can either hold this knife maybe like horizontally, something like that. Let's say this is your knife. This is the cross section of your knife, by the way. So, or you can hold your knife something like this. And then move like the knife with each of these configuration to the right, all right? So again, this is a piece of butter and you're trying to cut it. So I want you to visualize which of these is easier to cut the butter. Is the one, configuration 1 or 2? Well, the answer is sort of clear, right? 1 is smoothly go through the material, but 2, you have to apply lots of force, and maybe the surface of the butter that you get is not as nice as you want, or maybe you get it as the way that you want it. So as a matter of fact, this angle that we talked, the rake angle, is we can identify it as like this angle, right? So, or the picture that I see it here, like the rake angle here, for this one, the angle is 0. And for this one, the angle is 90 degrees. So the first thing that we realize is that the smaller this angle, the rake angle, we need larger force. So now with this analogy, let's, but also we have something in between. Maybe we, like the configuration we use is something between 45 degrees or something like that, which in this cutting process, in this actual cutting process of metal, like this angle is approximately around maybe 30 degrees. All right, so we can have anything between that. But this example is just, this example of butter is just a very extreme case. So starting with this analogy, let's look at the mechanism of removing material, all right? Again, let's see the parameters that we can think of when we are cutting a piece of metal. And I'm just talking in general. Maybe you're just using a chisel or maybe a knife or something, like in general, the process of removing material. So let's say this line over here, approximately on this shape that I'm showing you, we call it the cutting surface, the surface that has been machined, right? So let's call it the machined surface. And this is the original line, all right? So this is the original line. So then I can, let's say if I continue this line, all right? So let's call this distance, let's call it T0. So the distance over here, we call it T0. The thickness of the material that we want to remove. What else we can say? Let's say this line over here, tangent to the tool. And also we talk about another line, which was sort of perpendicular to the surface that we are machining. And we call this one rake angle, right? So this one is rake angle. Also, it is very common that our tool, because we want to prevent friction, is not exactly touching the surface of the machine part. Otherwise, it's going to rub against it and it's going to get hot and also maybe damage the surface. This very, very small angle, let's call it relief angle. All right, so that's about it. Again, this is our tool, it's obvious, and the workpiece as well. We know what is the workpiece. What else we can say? I draw a line perpendicular to the tool surface, like this line, and this angle is 90 degrees, all right? And let's call this line, well, because this line is the line that, if you remember, I told you the material being on top of, like layer by layer on top of each other, their shear stress is getting to the plastic and they are getting removed. Like, as a matter of fact, we have all these like shear layers here, like these layers has been removed and shear on top of each other. So let's call maybe this angle shear angle. All right. What else we can say? Well, the part of the material that has been removed and starts separating from the main part, we call it chip. So let me get rid of these lines. All right. So this is what we call like chip. And this chip has a thickness. So let's say the thickness of this chip, like this distance, we call it, let's call it TC, or the thickness of the chip. Or maybe I'm just writing out the chip thickness. All right. Now on the image on the right side, just put parameters for them. And these parameters are very common if you check different books. On machining, people use these parameters usually when it comes to the parameters for machining. We use phi for shear angle. We use epsilon for relief angle. Some people call it clearance angle, but relief angle is very common. Phi is the shear stress, and rake angle, we show it by alpha. All right. So the chip thickness, so you can say this is probably maybe closer to this area. This is the chip thickness, and the chip thickness, we show it by TC. And as we said before, T0 is the initial thickness that we plan to remove from the material. We introduce a new parameter, let's call it R, and R is T0 divided by TC. And we call it the chip thickness ratio.
Just a quick question.
Sure, go ahead, please.
Isn't the rake angle equal to the shear angle?
No. Rake angle is an angle that we can control when we basically we set up our tools. Oh, that's a good point. Thank you for bringing it up. Let's, to make it as a like general, for now, let's forget about this angle being 90 degree. Thanks for bringing that up. So that's just, I'm mentioning a special case when it becomes 90 degree. So the shear angle is not necessarily equal to a rake angle. Shear angle, we'll calculate it in a moment, can be equal to rake angle, depends on the angle that we set up, but it depends on the material. And yeah, please remove that 90 degree situation there. It was just a special case. All right. So it's not. So always, it's not always equal. It can be equal to rake angle, but it's not in general. Right? Does that answer your question?
Yes, that's good. Thank you.
All right. Yeah. So again, please forget that 90 degree here. As a general case, the shear angle is an angle which, let's say this is a layer that material has been removed. So layer where shearing stress removes material. All right? Which we will calculate it in a moment. All right? So R then is T0 and TC. That's one relation that we have. And based on the geometry, we can write down that tangent of phi is equal to R cosine alpha divided by 1 minus R sine alpha. This is like a geometrical relation. The proof is in your textbook. You can check it up. It's based on the parameters that we have here. So looking at this relation, we can say in general, if alpha decrease, like smaller alpha, when I'm using this sign, it means, like it's become smaller. Then looking at this relation, we can say that what's going to happen to phi? Phi, so smaller alpha from that relation, we can guess that phi also is going to decrease. All right? So phi is going to decrease basically, which we'll see the effect soon. So now, why it is important for us to find out how phi is changing? To answer that question, a guy named Merchant developed an equation which is famous for Merchant's theory or Merchant's equation. And it says that this angle phi in general is equal to 45. It proves it. Again, it proves, you can look it up or you can check your textbook. Plus alpha divided by 2 minus beta divided by 2. What is beta? Beta is called the friction angle. The friction angle, and it is equal to tangent, inverse tangent of mu, which mu is the friction coefficient. Friction coefficient between the tool and workpiece. All right. So this is an important relation that we should remember. How phi is changing when we change alpha and beta. So let's look at this equation, and by looking at this equation, we can say that if, let's say, alpha decrease, becomes smaller, or beta increase, the friction increase, more friction, then we are going to end up with a bigger, with a smaller phi, right? So I'm going to end up with a smaller phi. Smaller shear angle. All right, so this is how it changed. But what does a smaller phi means? So this theory, this Merchant theory, says that the stress can be found from this formula: tau equal to G 1 over tangent phi plus tangent phi minus alpha. All these relations are like geometrical relations, and some also experimental relation. The proofs of these sometimes can be long. It's not part of requirement for this course, but if you are interested, you can Google Merchant's theory and find papers that shows like this formula, the proof for this formula. We just use them in this course. And also we use them to understand when we change different parameters, how the machining process can change. And these relations, like this Merchant's theory and Merchant's equations, are very important among people who study machining process. They are very simple, but they are very important. So looking at this formula, we can easily show that if phi is small, so if phi decrease, which we know what can cause a phi to decrease, right? A smaller alpha or bigger friction, then the result is going to be larger stress. And larger stress, in fact, it means we need larger, basically cutting force. And also when we have larger stress, it can be proved that the temperature increase, more heat is going to generate, more heat generation. And more heat generation, because considering machining heat as an enemy for the workpiece and for the tool, and that's bad. And again, this formula shows what at the beginning we show for that butter one, right? And you see this is the effect of this alpha. Friction is sort of clear. The more friction is bad. It means more force, more cutting force, and more heat. Smaller alpha also, which on that extreme case when alpha is like getting to 0 degree, we need larger force, like that extreme case. All right. So is there any questions so far for this?
Can you please indicate once more what is alpha and phi on the diagram?
Yeah, let's go back to this diagram. And by the way, as you requested last time, some of you requested, I post all the blank slides the night before for each module. So if somebody wants to write notes on the blank slides. All right. So this is the picture that we have. And again, to remind you, this is as a general machining process. And by machining, we just, for now, we just mentioned removing materials by a tool, by a sharp tool. All right. And the parameters that we set, maybe let's look at this schematic on the right side. So this is our tool. Alpha, the rake angle, is the angle that you can see here between the surface of the tool and the line perpendicular to the machined surface. All right, this is alpha rake angle. The epsilon is obvious, is an angle which called relief angle, because we don't want a portion of our tool to touch the surface because it's going to generate heat and increase friction. Right? It's a small angle, maybe 1 or 2 degrees. TC and T0, they are obvious, and the ratio are T0 over TC. This phi, which you guys asked, this, as I said, it's not necessarily is perpendicular to this surface, like this shear line. And it can be any angle which we can calculate it now. How people calculate phi? So let me write it down here. Like in practice, we set up alpha. So this is our decision. What do we want for alpha, the angle, right? That knife things when we cut butter, that's our decision. We can measure TC. This is something after we cut, we measure the chip thickness, and it's very common in machining, people measure the chip thickness. And T0 is, again, is the depth of cut, something we decided, right? Depth of cut, we set it. So if we have T0 and TC, we have R and we have alpha, so we can find out phi. Phi is the shearing angle, all right? So phi then depends on alpha and R. It can be equal to alpha, but it depends on all these parameters. In general, it's not equal, all right? Is it clear now? I hope, right? So now with this mechanism and with these like parameters that you have, let me play that video one more time. Now maybe you appreciate more that video, right? So the tool is moving, removing the materials, and the materials gets to the plastic deformation, it breaks. Basically, the chip is forming, and so as you could see, it shows it so nicely that you feel like it's butter, but in fact, it is cutting. It is HSS tool is cutting steel, stainless steel, in fact. Right. So we review that one. Now that we have a basic understanding of mechanism of removing material, let's look at the machining operations. Machining operation involves a tool, again, removing material, but it can have different forms. Like in these 8 images that I show, like are the most common, but necessarily they are not the only machining process that we have. So the first one on the left on the top, so it is called turning, which the tool is fixed. Usually the tool is moving, is fixed, it's not rotating, the workpiece is rotating, but the tool is moving to the left and it removes the material. The second one is another turning process, but with the type of tool that we use, we cut off maybe a portion of a shaft. So it is called cutting or cutting off. So this is then cutting off process. Drilling, many of you guys are familiar with it or have done drilling, of course, in the past. This process on this image on the top right, it is called tapering, and which is very similar to turning. It's another turning process, except that this time this tool is moving X and Y, so we get a slope sort of. At the bottom, over here we have milling process, like the first one, it's called peripheral milling, and this one is called end milling, or some people call it pocket milling, because you are creating a pocket in a part. So this process over here, it has a funny name. It is called boring, but it may not be that boring. So the process is, in fact, making a hole that you have already made it by drilling bigger, right? So making a hole larger. Because with drilling, we have some limitation. We cannot go with a very large, let's say, diameter drill bit. And then the last one, as the like a schematic shows, it's the threading process, which is another type of turning process. All right. So what we want to do in this module, we are not going to study all of these. We're going to focus on turning process, and also we are going to study these two milling process. All right, which both of them, they are the same. But those are the most important, and the rest, they are very similar. You will see, and you can study on your own, but you don't need for this course. All right, the objective for us for this course is to study turning and milling process, and just the basic again. If you are interested to learn more, we have a grad course, which the entire course is spent on drilling and turning and milling process, these three process, and it's a grad course. Hopefully, if you decide to go to a master degree, to do a master degree, maybe you can take that course. All right, but those courses focus more on theory. Here, we just need a foundation to get a job done. If we decide to do a turning process, we need to know the parameters and so on. Let us start with turning process. Again, as I said, turning process, the main definition is that the tool bit is fixed, right? And it is the workpiece that rotates. That's the difference between milling and turning, all right? So this image shows a lathe machine. Many of you have worked with this machine, or at least you have seen one in our mech machine shop or maybe somewhere else, all right? So in this schematic on the right, it shows like the tool that being, the workpiece that has been secured and clamped in the chuck, and the chuck is rotating with N, the rotation speed, and the tool is moving with speed F, which we call it feed speed, and we are removing material. So let's say our initial diameter of these workpiece is D0, and our final diameter we want to get is DF. That's the whole process of turning, all right? And also over here, this small d is the difference between DF, D0 divided by 2, which is called the depth of cut, okay? Sorry, that's my phone. So that's a funny things, working from home or teaching from home is these sort of things that happen. In summer, I had a course where my fire alarm start on, and then I had to leave, but the students, they were safe and they could stay in the class, in fact. Well, so let's not wish that the fire alarm goes on, or maybe so you could sort of stop this class. All right, but let's look at quickly at the turning parameters, all right? So let's go step by step. On the image on the top left, again, we'll see the same workpiece and the tool bit. The feed, all right, we show it by F. And feed, keep in mind what we call feed is the displacement per, let me write it down here, the displacement per revolution. So displacement per revolution. All right, so it's not the linear speed then. So this is what we call then feed. So the unit is then millimeter per revolution or inch per revolution, all right? So if you want to find out, let's say the linear speed, all you need to do, you just multiply F, the feed, by basically the N, all right? This F, in fact, is the feed, and N is the RPM. So you get the unit of, maybe for this one, millimeter per second. Let's say if n is revolution per second. Okay. So what else? The depth of cut, as we said, is the difference between the two diameters. Now I want you to visualize and think that if we rotate this workpiece 90 degrees, right? What we will get is an image in this left bottom corner. Okay, this image over here, right? All we did the same things, we just rotated 90 degrees. And but why we do that? Now if we focus on this part that we are removing the material, all right? So this portion again, we can match it with what we just learned for the mechanism of removing material. All right, something like that. You recall this one, which in a moment we just saw it for, in general, the mechanism of machining, all right? So the only difference here is that, let's see how we can match these parameters. Let's start with this depth of cut. This depth of cut here, all right? Now this depth of cut for us in this image, we can think it is like this distance, which is in fact the width of this cut over here. Like this mechanism that I showed. What about this distance over here? What we call it the feed, all right? This feed, if you look at this image and the initial image that we had as a general for machining, we can now say that if this distance is f, right, per minute, sorry, not per minute, per revolution, this f in fact is this T0 over here. What we call the depth of cut in the initial mechanism, right? Don't worry if these parameters confuse you, soon you become familiar with how these things working, right? What I'm trying here to do now to show you that this turning process in fact is very similar to the mechanism that I just showed you. So the mechanism we studied, what parameters we had. We had alpha over here on this image, which we call it rate angle. We have basically phi, which is the shear angle, right? What we call it shear angle. The chip is the same chip. TC for us is the chip thickness. Again, no difference. And T0 now here for us, T0 is the feed. That's the only difference that we can see over here. V is the velocity, the linear velocity of the tool. And the rest is basically similar. So in fact, we can go back and use the same formula that we just learned for a turning process. All right? So far, are we good? If there is a question, please let me know. I'm just going step by step slowly. Sorry for some of you are familiar with this and it's bore you, but bear with me. We'll make a nice conclusion soon. Is there any questions so far, guys? Are we good? And one more thing here on this first image on the top, please pay attention. We have three forces. We have in fact one forces which has three components because we are in a 3D sort of mode here. If we get the component of the cutting for the force, we divide them to tangential component, radial component, this FR, the tangential component, FT, and FC, which is the cutting force. So this FC, this one, we call it cutting force, and we show it by FC. And this parameter is important for us again, because that's what determines how much power we need to cut a certain material with a certain speed. All right. So if you're okay, let's move forward one more step. I'm showing the same schematic. We have a workpiece rotating, let's say, with a rotation speed n, all right? Let's for now keep N to be the common unit, RPM, revolution per minute. All right. And what else we have here? We have the feed speed, let's call it F. And again, F can be a millimeter per revolution, or it can be inch per revolution. All right. And again, keep in mind, this feed speed is different than linear velocity. If I want V, the linear velocity, how this tool is moving, how fast this tool is moving, I just need to multiply this F by N, all right? Then it gives me, of course, if this N is RPM, revolution per minute, it gives me the displacement per minute, the speed of this tool. DF, our final diameter, and D0, our initial diameter. So the depth of cut is the difference between these two. So let's show it by D, and this D, we can write it as D0 minus the final divided by 2, right? Don't forget this divide by 2 things, all right? So we introduce here another important, not parameters, and a value which depends on these cutting parameters, which we call it MRR, which is material removal rate. In simple words, we can say the MRR is the amount or the volume of materials that has been removed in 1 second or in 1 minute or whatever unit of time that we decide. So it's not again per revolution. It is the amount of material being removed per unit time, all right? So let's see if we can calculate it. Can I write that let's say in one revolution, we remove 1 ring, right? Imagine 1 complete revolution, we remove 1 ring, something like similar to, let's say, if I can draw something for you. That makes sense. So, sorry if I'm being slow, I'm getting used to this digital writing. So for many years, I was used to using blackboards and whiteboards and document camera, but now these digital things. All right, so maybe I'm just exaggerating here, but let's say in 1 revolution, we are removing 1 complete ring, all right? So in this image, we know that this ring, let's say this is the internal diameter, which is dF, and this guy is the D0, right? So what is the thickness of this ring? Well, because we said 1 revolution, right? If we said 1 revolution and our speed is F, so this distance must be F millimeters or F inch. That's correct, right? So what is the volume of this ring? The volume of this ring, we can easily calculate it. It's pi over 4 F and D0 2 minus D1 2. All right, so I can simplify it by writing pi F, then this one I can write it D0 plus D1 divided by 2, and this one I can write it D0 minus D1 divided by 2. I just manipulate these to get a nicer maybe formula. So what I get, pi F, let's call this one the average, and this one we know what it is the depth of cut, all right? So what we calculate is volume of the material that we have removed in one complete revolution. So then from here we can say in n revolution, the volume is going to be, we just multiply it by n, right? N pi f, the average, and then we're going to have d, all right? And we know n revolution per time, right? Per unit time. Okay, and this is what we called MRR. So summarize material removal rate, then it is N pi F, the average, multiplied by D. That's our final formula that we have. Okay, because we said in 1 unit of time, we are going to do n revolution. So this is the amount of material is going to be removed in 1 unit of time. So is there any questions so far, guys? Are we good? So it seems very simple, right? So again, don't forget, if you have the velocity here, we have a formula, velocity, linear velocity, which is F multiplied by N, right? So this formula, you can replace it, N multiplied by F by velocity pi D average multiplied by D. Let's solve one quick example before we end today's session. And today it was mainly a lot of introduction. Hopefully next session we'll do more things. So we have a lathe operating, all right, and we're cutting aluminum. So that's the question. It says the initial diameter is 2 centimeter, all right? And the depth of cut is 0.2, our RPM, 500 RPM, and our axial velocity is 0.4 millimeter per second, all right? So here we have V. So we have V, let me write it down over here. So we have V 0.4 millimeter per second. We have N, so I can write MRR. Our formula was pi F N, the average, multiplied by depth of cut. So pi is pi. F multiplied by N gives me 0.4. The speed already, I have it there. The average D, so initial diameter is 2 centimeter, right? And so let's convert it to millimeters. So it's going to be 20 plus 16 divided by 2. And the depth of cut is 2 millimeters, right? So our D0, let's see, I haven't done a mistake, 20. And our D final, if you want to have a depth of cut of 2 millimeters, so it means our D final will be 16 millimeters, not 18, right? So we putting these numbers together, I guess, but check my calculation again, please. I guess it's going to give you 45, or do the calculation later, whatever it's going to be. And the unit is going to be, so because we use millimeter, it's going to be millimeter cube per second. The amount of material we remove in 1 second, all right? So is there a question so far, guys?
Quick question. Shouldn't the feed rate be millimeters per revolution?
So as I said, feed is, like the feed here is, so as Ahmad pointed out, feet is revolution, is millimeter per revolution, all right? But here in this question, what we have the linear velocity, all right? So, and V, linear velocity, is F multiplied by N. So that's why in this formula, I just replaced this F multiplied by N by just 0.4, right? Is it clear, Ahmed, or no?
Yes, that's fine. Thank you.
That's why I said,
And
I emphasized, make sure in a question that what information do you have? Do you have the axial velocity, or the linear velocity? That's millimeter per second, or the feet. The feet always is millimeter or inch, doesn't matter, per revolution. How much the workpiece is moving in one complete revolution, all right? So what is their relation? So F multiplied by N give you the linear velocity. All right, guys? All right, so please watch the video that I posted a few days ago as pre-lecture activity. We need them for next topic when we talk about the power requirement to do cutting, and also repeat the same things. We're going to repeat the same things for milling process. And yeah, and also review what we learned so far. I know it was very simple, but that's the foundation. You need to get a good grasp of these before we move forward. And also all these notes I will post, and the blank slide as well, which you can get an idea of what will be our next topic, which we're going to discuss how the cutting force and the power requirement change if we change any of these parameters, which I'll put a video for you guys as a pre-lecture activity. Hope you watch it. If not, please do it by Thursday, which in this experiment, we've seen how changing this parameter is going to change the cutting force. All right?